So the more realistic use of limits and functions is in cases where the direct substitution into the function will result in the limit being 0 over 0. And when this happens, we have to use a different method to determine the value of that limit. So if we take a look at this limit, so we want the limit as x approaches 2 of x squared minus 4 over x minus 2. And if we plug this in right away, so if we wanted the limit as x is approaching 2 of 2 squared minus 4 over 2 minus 2, we would see that this would end up being 0 over 0. And so we can't actually define this limit. So what we need to do instead is we need to simplify this function so that we have the limit as x approaches 2, and I'm going to use difference of squares on the top. And after I've done that, then I can simplify my expression. And then I'll have the limit as x approaches 2 of x plus 2. After this, I can use properties of limits to understand that that's actually the limit as x approaches 2 of x plus the limit as x approaches 2 of 2, which is 2 plus 2, which is 4. And if we look at this graphically, we would see that we have a function that has a hole at the point when x is 2. So we would have a hole right there. And we know that from this information here. Okay, so in these instances, we have to use simplification, some type of simplifying strategy, in order to first simplify the limit and then evaluate it. So let's try another example. So we'll have a look at this limit. So right now, if I were to just put 5 in for this, I would end up with a 0, at least a 0 on the top. And actually, if I think about it quickly, I would have 25 minus 20 minus 5, also a 0 on the bottom. So I can't do it as is, so I'm going to have to simplify. X approaches 5. And a good thing to remember is that because I know I need to simplify, I'm probably going to have this on the denominator, this x minus 5. And 1. Okay, now that I have factored that, I can eliminate my like factors and rewrite my function. And now I can sub in and solve for the limit. So that will give me the limit as x approaches 5, 1 over 5 plus 1, which equals 1 over 6. Okay, let's try another one. So in this one, I have a function and I want to know the limit as x approaches 9. And I'm not going to be able to get not 0 here, so I'm going to have to do something. And I have the root of x and 3 on the top, and then I have x minus 9 on the bottom. So this one might not be super obvious, but if I take the difference of squares here, so the square root of x is root x, and the square root of 9 is 3. So if I did a difference of squares on the bottom, then I would get some terms that I can cancel. And I would be able to write out a simplified function. And then sub in for the actual value of the limit. I'll do another one. In this one, I've got 4 minus h squared minus 16. Oh, and I'll divide it by h. Well, I know right away that I'm going to have to cancel out this h on the bottom because I can't divide by 0. So I see here that this is a squared term and 16 is a squared term. So I'm going to start by taking a difference of squares. So I have 4 minus h as the square root of 4 minus h squared minus 4 times 4 minus h plus 4. And that'll all be over h. And I'm just going to simplify in the brackets. 4 minus h minus 4 is 0, so that's just h. And 4 minus h plus 4 is 8 minus h, all over h. Now I can cancel out those, and I can solve my limit now that I no longer will get a 0 on the bottom. So I have negative 8 minus 8 as my simplified form. And so I'm going to end up with just negative 8. Okay, last one. I'm going to look at the limit as x approaches 1 of 1 over x minus 1. And in this one, I can't actually do anything to make this not a 0. Like I can't simplify this any further. So in this case, this limit just does not exist. For practice, you should do page 19, numbers 4, 5, 6, 8, and 9. If you ever want to check your work, you can always use Desmos to see if your limit is correct.